How to derive Cp minus Cv is equal to R for an ideal gas. Now what is Cp? What is Cv? Of course R is a constant. Cp or C subscript P is the principal molar heat capacity at constant pressure. And then C subscript V is the principal molar heat capacity at constant volume. Now what does all this mean? Before we get into the derivation, I would like to explain what these two mean. First of all, C stands for specific heat capacity of a substance, and specific heat capacity of a substance is simply the amount of heat that is necessary to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. So when we say C subscript P, it means we are talking about the specific heat capacity of a substance at constant pressure, or call it the principal molar heat capacity at constant pressure, and then the principal molar heat capacity at constant volume, or you may call it the specific heat capacity of a substance at constant volume. Now take note, when a substance is being heated, pressure and volume are always affected. When it comes to liquids and solids, the pressure and volume are affected, yes, but it is always in negligible amounts. That is why we never consider the changes in pressure and volume when we heat a liquid or a solid. But when it comes to a gas, when you heat a gas, for example, its pressure will increase significantly and its volume will also increase significantly. So the changes to pressure and volume when you heat a gas are too big that you can't ignore them. So that is why when we are dealing with a gas, we have to first hold one of these constant. We shall heat a gas and first hold pressure constant, and also we shall heat the same gas and hold volume constant. And so that's how we come up with the specific heat capacity or the principal molar heat capacity of a gas when the pressure is constant, and then the principal molar heat capacity of a gas when volume is constant. So in our derivation for Cp minus Cv is equal to R, we are going to first of all heat a gas in a container and first keep pressure constant. Then we shall use the first law of thermodynamics to get an expression. Then we shall do the same. We heat a gas, keep the volume constant, and then we shall use our first law of thermodynamics to get an expression. Then we shall compare those two expressions to come up to this. So let's get started with the derivation. Now to get started with the derivation, now let's look at what happens when we keep the volume constant. Now right here we are having a container, and in this container we are having a gas. This gas is subject to heat. When we subject this to heat, definitely, of course, this heat is going to be picked up by these molecules of this ideal gas. Remember, when we are talking about an ideal gas, we are talking about a gas where the total internal energy is equivalent to its entire kinetic energy. In our previous session, we said that when we are dealing with an ideal gas does not have intermolecular forces of attraction, and because it doesn't have intermolecular forces of attraction, therefore its total internal energy is only and only comprised of the kinetic energy, since the potential energy is zero. And so it means the internal energy of this gas, because it is an ideal gas, is equivalent to the kinetic energy of the gas. In our previous session, we went ahead and derived the expression for the total kinetic energy or the total internal energy of an ideal gas. So when we keep the volume constant, from the first law of thermodynamics, which is that the heat given in Q is going to be equal to an increase or the change in internal energy plus the work done by the system onto the surrounding, we know that our value of Q in this case is going to be this: specific heat capacity at constant volume times change in temperature. Now where does this come from? Now, as you may be aware, we know that Q, which is heat, is going to be equal to mass times specific heat capacity times change in temperature. Now here, this is an ideal gas and we are dealing with 1 mole of an ideal gas. Now since we are dealing with 1 mole of an ideal gas, it means our value of M, the mass, is 1 mole. So this is going to become 1 mole times C Now, since this is happening at constant volume, so meaning that our specific heat capacity here will be CV, specific heat capacity at constant volume, or principal molar heat capacity at constant volume, multiply that by the change in temperature. This is going to be equal to Q. So this value of Q is what we replaced this Q with that. That's how that comes to that. So we continue our change in internal energy. Our internal energy in this case, remember we're dealing with an ideal gas, so our internal energy is going to be 3 over 2 RT. Of course here it is 3 over 2 R times change in temperature. Of course, from our previous expression, this we derive this as 3 over 2 nRT. Now our value of n here is 1 since we are dealing with 1 mole of an ideal gas, so that's why it's going to be 3 over 2 times R times the temperature. The temperature is in this case represented as the change in temperature. Now, of course, because our volume is constant, it means that this gas is not able to expand because it is in a static container that is not allowing this gas to expand. So it simply means that all the heat that is given in is going into increasing the kinetic energy of these molecules, or the internal energy of these molecules of the gas. So it means that as far as this is concerned, when we keep the volume constant, it means that this is not able to do external work. So it means that our value of work there is 0. So that's why this the substitution for that is going to be equal to 0. Of course, when we continue with this kind of expression, when we divide change in temperature on both sides here, CV dt, change in temperature on both sides, this goes with that. They cancel out and we remain with our CV being equal to 3 over 2. And that formulates our first equation. So this is the first expression we get when we keep the volume constant. So we are going to go ahead and keep the pressure constant and get another expression. And we see how we relate that expression to this expression. Now, when we keep the pressure constant, of course, we subject this system to heat. When we subject it to heat, of course, this heat is going to be picked up by these molecules, and the pressure inside here might want to increase. But to keep it constant will require that this system is supposed to do work against the surroundings. So it means that this piston will be pushed up from this point to that point. And so this piston will move up through a certain distance d. So when this piston moves up through a certain distance d, we say that this system has done work on the surrounding. And we know that work done is given by force, the force by which this piston moves up, times the distance this piston is going to move, which so happens to be d. So, of course, let's get started now. When we do this now, it means our Q, this is the first law of thermodynamics, in the context that with which it was introduced to you in our earlier session. So when heat is given in, is going to give us an increase or a change in internal energy, plus work will be done on the surrounding. So our value of Q here, which is the Q, is given by Cp times change in temperature. How does this come about? Of course, we are going to get this just like before. We know that heat, Q, is given by mass times specific heat capacity times change in temperature. But in this case, we are dealing with 1 mole of a gas. So this mass is represented by 1 mole of a gas. So meaning that our value of Q is going to be 1. Multiply that by specific heat capacity, or in this case, our specific heat capacity, since we are dealing with it at constant pressure, so it means that it's going to be specific heat capacity at constant pressure, or call it the principal molar heat capacity at constant pressure. Multiply that by change in temperature, and this is the expression for our value of Q in this case, and that's how this Q gets to be substituted right here. So this Q is C subscript P times change in temperature. That's going to be equal to the change in internal energy, just like I had explained before. Our change in internal energy is equal to 3 over 2 R dt. This is the expression for internal energy of an ideal gas. We derived this expression and explained where it comes from in our previous sessions. So it's going to be change in internal energy times which is 3 over 2 times R times T, plus the work done. Of course, work done is force times distance. In this case, it's the force applied by the piston times the distance, this distance that is covered, which so happens to be the change in distance, which we've denoted by delta T. So to continue from this step, we continue this Cp times delta T is equal to that, plus, now force times distance. If you look at this, our value of force has been expressed in terms of P times A right there. Our force is pressure times area, which is times then the change in the distance, which so happens to be that. Now, where is this coming from? We all know that pressure is the force acting normally per unit area, so we know that pressure is equal to force over area. Definitely, when we make F the subject of the formula here, F becomes pressure times area. And that's how we go to substitute for the value of F right there. So this is pressure times area times change in the distance, which is right there. So from this step to go to the next step, this happens, this is the same, is going to be that, which is that, times, now when you look at this still, if you look at area times the change in distance, it's going to give us something else. It's going to give us volume. If you look at area, remember this area we're talking about is the area of this piston, the cross-section area of this piston. So when we get the cross-section area of this piston and multiply it by the distance moved, cross-section area of the piston times the distance moved is going to give us the volume of that portion that the piston moved in. So area times change in distance, this is giving us a change in volume. That's the change in volume from this point to that point. So that's how this comes to change in volume. So it becomes pressure times change in volume. So to move on from this step, we get to the next step. Of course, these others are still the same. Still here, this is PV. Now PV is the same as RT. This is coming from the ideal gas equation. We all know that the ideal gas equation, PV is equal to nRT. Now, since here we are dealing with 1 mole of the gas, our value of N is 1. So it means that PV is going to be equal to RT. And this is exactly how we substituted for this. So our pressure times volume is going to be equal to R times T. Pressure times change in volume is equal to R times change in temperature. So you end up with an expression where we are having delta T, delta T, delta T. Of course, when we divide through by delta T here, by delta T there, by delta T there, all through, this will go with that. They all cancel out, the delta T's. When the delta T's cancel out, we remain with Cp is going to be 3 over 2R, which so happens to be that, plus R, which so happens to be that. Now when we have this expression, in our first expression, when we made the volume to be constant, we ended up with Cv being equal to 3 over 2R. So from our first equation 1, which so happens to be that one, Cv, which so happens to be this, is equal to 3 over 2R. So this 3 over 2R, we substitute it right there. And so in our next step after this one, you find that our Cp is going to be equal to Cv plus R. And when we make R the subject of the formula, Cv comes this way. We end up with Cp minus Cv is equal to R. And that's how we get to that derivation. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.